So far, we have defined a derivative of the field. So if you have a field, its derivative field is k entries, k going from 0 to, let's say, n minus 1, or whatever the dimension of this vector is. And the derivative is defined as a matrix operation, where you take lth component multiplied by a matrix which is shift minus unity. It's a matrix, it has two indices, KL, and we sum over L. Once we have that, it's very natural to look at the magnitude of that thing, just like when we have F, it's natural to look at F squared. So let's look at the vector phi times the transpose of the vector. So if this is a column, the other guy is a transpose. That, by definition, is matrix I acting on phi, the whole thing transposed, dot matrix sigma minus unity, shift minus unity acting on phi. Now I can take a transpose, so I can make this phi transpose. And then I have a transpose of this matrix times matrix itself, phi. So that's a matrix, and it's sandwiched between the vector phi and the transpose of the vector phi. We already had a second derivative, but it was forward second derivative. The second derivative will be nicer. It's related to the other one, but it will be nicer. And we'll call this combination here a matrix. We'll use a box to denote a Laplacian. Sometimes people use lambda or inverse delta, and God knows what. It's a second derivative, so dimensionally it's 1 over lattice spacing square. We sum over all directions in the dimensions. So it's sum of the shift in mu direction minus 1. And to remember, transpose was same as the inverse, so this is minus 1. Sigma mu minus 1. Summed over all dimensions. And it's convenient to put, for positivity reasons, etc., to put a minus here. So this Laplacian, what we'll call Laplacian operator, just n by n matrix, we can multiply out. When we multiply these two guys, we get unity. When we multiply these two guys, we get unity. So we get unity twice. And then we get two cross terms, mu times that, and mu times that. Minus sign is this minus sign, and we get the sum of going to the left and sum going forward. So this is shift operator. I'm adding up, stepping this way or that way. And if you write it out, it's quite nice, because on diagonal I have minus 2, minus 2, minus 2 all the way. Off diagonal, from here I have 1, 1, 1, 1. The inverse is below the diagonal, so it's 1, 1, 1, 1. Periodicity puts this extra guy to this corner. This one has to be put in this corner, and everybody else is 0. So what it does, Laplacian measures curvature. Why is that? Think of 3 points. So you're at L minus 1 point, at point L, and L plus 1. If I take average of the value here and here, the guy to the right plus value to the left, and compare it to the thing in the middle, If the average of left and right point is exactly in the middle, then we can draw a line through this point. So this is flat. But if the average of the left and right point is different than the point in the middle, then we have a curved situation. We're either curving up if the average is high or curving down if the average is down. So that's what the Laplacian does. It measures curvatures.